Terrific. Okay, well, we have our third talk right now before the lunch break. We're going to be hearing from Kotaro Tanahashi from Recruit Co., and he's going to be talking about their use of the D-Wave systems in optimizing TV commercials. So thank you, Tanahashi-san. Good to see you.
Yeah, good to see you again.
Okay, let's thank our speaker.
So, hello, everyone. Thank you for giving me an opportunity to talk about my project on TV commercial optimization. So before we begin the presentation, let me introduce myself and our company. I have been working on the applications of quantum annealing since 2015 with Shu Tanaka from Keio University. And we are mainly focusing on the digital marketing. And we also developed the software tools like PyCubo, which is very useful to create cubometrics from the expressions. And PyCubo is included in the D-Wave Ocean SDK, so please try using it if you're interested. And Recruit is a company that has a wide variety of the web services, like hotel reservation services or job searching website. Here in the United States, Recruit operates Indeed.com and Glassdoor. And our mission is to realize the matching between users and business clients through the technology. And I believe that the quantum annealing plays a very important role in this mission. So today I'm going to talk about the project of the TV commercial optimization using the D-Wave CQM, a quantum classical hybrid solver. And we determined the assignment of the TV advertising to the time slots using the D-Wave CQM, and we actually broadcast the TV commercials based on the optimization results. And we also confirmed that the D-Wave CQM outperformed the other solvers, and including the existing manual method. And this is an evaluation using the actual user behavior. So first of all, let me explain the market size of the TV commercials. So nowadays, the internet advertising is rapidly growing. However, the market size of TV commercial is still large. And I think TV commercials' role in advertising is kind of different from the internet advertising. And TV commercial is maybe useful for like brand recognition, promoting some brands or promoting the brand recognitions. So Recruit is one of the companies that spend a lot of money on the TV commercials as well. Okay, so there are two main players in TV advertising: TV networks and advertisers like us. And TV networks sell time slots to TV advertisers. And what they are doing is to try to maximize the total profit with limited inventories. And on the other hand, advertisers like us purchase time slots from the TV networks to air the commercial. And we try to maximize our own KPI, such as GRP or reach, which will be explained later. So as far as I know, the first success of the optimization applied to the TV commercial was reported by the NBC, one of the biggest TV networks in the United States. They try to maximize the total profit with limited inventory using the integer programming. They actually increased the revenues by over $200 million. And I thought, maybe I can do something like this. So from now, let me explain the optimization for advertisers like us. The GRP is the most common KPI for advertisers. This measures the impressions impact of TV commercials, and it's defined as the sum of view counts or sum of view rates. But there's a problem in GRP. For example, so let's look at this example. In the left case, only one people watching the TV commercial 3 times. But in the right example, 3 people watching TV commercials only once. But in both cases, GRP is calculated as 3, even though the situation is totally different. To solve this problem, another KPI named reach was proposed. Reach is defined as the number of viewers who watch advertising at least once. And reach indicates the broadness of the viewers watching the advertising. And we can now distinguish these 2 cases by using reach. And also we can extend the reach to more general case. There is another KPI, N-reach. And N-reach is defined as the number of viewers who watch the advertising more than N times. So we introduce the threshold here. And reach can be considered as a special case of N-reach when N equals 1. And finally, for in advertising, TV commercial advertising, it is very common to have multiple versions of advertising. And for example, if I want to promote some product, and product has some multiple features, in that case, I can create 2 advertising. And one is introducing 1 features of the product, and the other advertising introduces the other features of the product. So I want to show all advertising to the viewers. So in such case, by maximizing the NO reach, I can realize what I want to do. And NO reach is defined as the number of viewers who watch all kinds of advertising at least N times. So in our project, I want to maximize this NO reach KPI. So now let's move on to the problem setting. As the input, we have an expected viewing ratio for each viewers and for each time slot. This estimated value can be calculated by some machine learning method. And also, we have a capacity for each time slot. And as an output, we determine the assignment of the advertising to each time slot. And finally, we evaluate the result of the optimization using the actual view data, which is collected from the device located at the viewer's TV. And also, so let's look at the formulation of NO reach problem. The problem we are trying to solve is a combinatorial optimization problem, which is also formulated as integer programming. Here we show the form of the integer programming format. And there are 3 decision variables. The X is a decision variable that indicates the number of impressions of the advertising A at the time slot t. So we want to determine this x. But there are other additional frog variables, z and y. And y is an additional frog variable that indicates whether the viewer V watched advertising A more than n times. So the y represents this. It indicates whether the view count is more than the threshold or not. And z is also the additional frog variable that indicates that each viewer watch all kinds of advertising or not. So in this case, this viewer watched all kinds of advertising, so the flag is equal to 1. So in this problem, we are maximizing the sum of z, which is the total number of viewers who watch all kinds of advertising more than n times. So let me summarize the flow of the optimization and evaluation. First, we sample the viewers out of all viewers, and we estimate the viewing rate based on the past data by using some machine learning method. We sample the viewers because if we use all viewers, we cannot handle it by this mathematical solvers. So we sample the viewers. And then next, we optimize to determine the assignment of the advertising. And next, we actually air the commercials, and we evaluate each method by using the actual data. Okay. And let me see the optimization solvers we used in the project. We used 3 solvers: CBC solvers, and IBM CPLEX, and D-Wave CQM. CBC solvers and IBM CPLEX are the mathematical solvers. They are very conventional solvers. And also IBM CPLEX is very competitive, kind of state-of-the-art solvers. D-Wave CQM solver is a kind of new solvers developed by D-Wave systems. They are combining QPU and GPU. This is a hybrid solver. I think the main feature of the CQM solver is to be able to handle the very complex constraints, even though they can handle the quadratic constraints. And because our program has very complex constraints, I thought the CQM solver is very suitable for our program. Also, we changed the sample size from 50 to 500. Here is the results of the optimization. So the y-axis here represents NO reach ratio for evaluation data. So this is a final evaluation score. So the higher is better. And x-axis represents the sample size of the viewers. So overall, CQM performs the best among all solvers, especially when the sample size is smaller. But here, what's the meaning of the sample size, x-axis? If the sample size is large, and then the problem size is also getting large, in that case, the solver cannot handle anymore. So the solution of the problem is getting worse. But on the other side, on the other hand, if the problem size or sample size is too small, in that case, the optimization overfits the very small portion of the viewers. In that case, also, the solution is getting worse. So for this reason, there should be some optimal sample size between here. And if you look at the graph, maybe 300 is the optimal sample size for CPREX and CQM. But we need to understand why CQM is so better. To understand why, we showed the objective function of the optimization. If you look at the objective function, surprisingly, there's no significant difference between CQM and CPREX under the 400 here. So why CQM is so better in the evaluation data, only in the evaluation data? So to understand why, maybe we need to understand the robustness of the optimization. The robustness in the optimization is actually can be seen everywhere. For example, if we have the objective function ax plus by, and a and b are some coefficients, and x and y are decision variable. If a and b are estimated values, maybe in the evaluation time, maybe a and b can be changed. So for example, in the case of traveling salesman problem, we estimate the duration time from one node to the another node. But this duration time can be changed, maybe because of the weather or traffic jam. So in the in the real application, there is some randomness. So in the robust optimization, consider this randomness. Okay. So we did experiments to analyze the robustness of the solution obtained by the CQM and IBM CPREX. We added the artificial noise to the estimated viewing rate, R, and we create the R hat. And we calculate the evaluation score by using this noisy estimated value. So we simulate the noisy situation by adding the noise, and we control the amplitude of the noise by using this parameter P. And we see how the evaluation score changes depending on the noise parameter P. Here's the results. X-axis is the noise strength P, and y-axis is the evaluation score. P equals 0 means there's no noise. When there's no noise, the score of the CPREX and CQM is the same. But if we gradually add the noise, increase the noise strength, and then the score of the CPREX is getting better than CPREX. So from this result, I can say that the solution of the CQM is more robust than the value of CPREX. Also, we can see the difference between the sample size is 50 and the sample size is 300. When the sample size is smaller, we see the bigger difference between CQM and CPREX. Maybe this explains why the CQM is better when the sample size is small. Okay? And some research argued that the robustness of the optimization is related to the shape of the landscape, energy landscape. And solutions around the sharp minima, like here, is less robust. And the solution around the flat minima, like here, is more robust. And also other research suggests that the solution obtained by the integer programming solver tends to be around the sharp minima like this. So this is just my hypothesis that maybe the solution of the annealing machine could be somewhere around flat minima. So that's why the solution of the CQM is more robust than CQM. And also, I have to mention that this local flat minima is very hot research topic in machine learning community. There are many researches about this in New Rips last year. So let me summarize our project. So we proposed the method to optimize the assignment of the TV advertising to the time slot. And then we actually broadcast the TV commercials, and we evaluate the multiple solvers using the actual data. And we confirmed that the D-Wave CQM performs the best. And it's actually better than the existing manual method by 90%. The marketing department in our company are very happy with this result. And I cannot say the actual figure increased by this optimization, but it has very big business impact. Also, CQM showed that the more robust solution than the solution of the CPLEX. And this suggests that maybe new use cases of annealing machines. Now, I think the most exciting part of this project is that actually millions of people in Japan watch the TV commercials optimized by the D-Wave machine. This is very exciting, isn't it? Thank you very much.